Algebra 2 Cram, New York State Algebra 2 Regents, Common Core, Basics, Trigonometric Functions, Concept number 24, Inverse Trigonometric Functions, the sine of an angle, okay? The odds of someone doing exactly what you tell them to do is pretty slim, but I guarantee that if you cram with me, you'll become an Algebra 2 master. What we're doing here is effective. I'm coaching you to turn your wants and desires of getting an A or perfect test scores into a brand new paradigm. I want to include everyone who needs a boost in Algebra 2, and if I could stick every single math student with a syringe containing a healthy dose of eye-opening awareness of their inner mathematical genius, I probably would. So inbox me at memedicine@gmail.com to get your healthy dose by purchasing the entire Algebra 2 Cram session beyond the trigonometry series. You have lots of peers, classmates, and colleagues, or friends who are taking Algebra 2 with you, and they could benefit from purchasing this entire Cram session as well. So be sure to spread the word and tell them to inbox me at memedicine@gmail.com. You'll be glad you told them because they'll make great study buddies. And last but not least, the concept of cramming often has a negative connotation, but what people are actually thinking of is hurrying, which is a result of fear and can consequently be destructive to your overall learning process. We're not hurrying here, we're cramming, and there is a huge difference. Hurrying is jam-packing tons and tons of unorganized information into your mental spiritual DNA over a tiny amount of elapsed time, whereas cramming is taking quantum leaps in your understanding in an organized way in what seems to have been instant, okay? So let's delve into concept number 24, inverse trigonometric functions, using sine as an example. Inverse trigonometric functions, the sine of an angle theta. How does one find an angle for a known trigonometric value? Definitely press pause and I'll give you a moment to think. So how would you go about finding the angle if you know the trigonometric value? All right, so hopefully by now you are able to press pause and arrive at an answer, and if you didn't, that's completely fine. Let's delve into this together. To find an angle for a known trigonometric value, we have to use the inverse trigonometric function, or an inverse trigonometric function. In this particular example, we're going to use the sine function, okay? Okay, so let's say, for example, we grow an acute angle theta in the positive counterclockwise direction, and it's in standard position in quadrant 1, okay? Because it's in standard position, it's going to have the following features. Its vertex is located at the origin. The ray on the initial side ray is on the positive x-axis. This is one of the defining features of standard position, and later you'll see reference angle definitions, okay? A reference angle is an acute angle whose initial side ray is on the positive x-axis, but we'll get into that a little later. That's like a sub-aside outside of this aside that I'm taking you on, okay? We also noted that the angle is acute, meaning its measurement is between 0 degrees and the quadrantal angle 90 degrees. When I say quadrantal angle, I mean the terminal side ray ends on either the x-axis or the y-axis. And this ray you see here is the terminal side ray for our acute angle in standard position. It ends in quadrant 1, or terminates in quadrant 1, okay? Then we're going to be cute and call this terminal side ray R for short. And we're also going to be cute again so that we can build our triangle, because without triangles, there kind of sort of is no trigonometry. Well, if there's an angle, there can actually be, but we're basing this on an imaginary triangle, okay? So in order to create our imaginary triangle, we're going to insert this point But we're going to call our point P, P being short for point, and our point has the coordinates X and Y, okay? So let's say that now this is no longer a ray, it's rather a segment length. We're going to resolve our segment length into its X and Y components in order to create our imaginary right triangle. So the extent of this terminal side segment length is X. So this is its horizontal extent, and it rises to the level of Y. So this is its vertical extent. So note that when finding trigonometric values, that if the x-coordinate is in quadrant 1 or 4, the value will be positive. But let's say we have a terminal side array that's over here, and we resolve it, and our x-coordinate ends up over here in the negative realm of the x-axis. This means our x-coordinate will be negative, okay? So this is why in some instances you might have a negative sine, cosine, tangent, cosecant value. The same can be said for the y-coordinate. Because the coordinate falls in quadrant 1, it's positive. The same thing if the quadrant were to fall, if the terminal side segment were to fall in quadrant 2, its y-coordinate would be positive. But if the terminal side segment ends up in quadrant 3 or quadrant 4, we're now in the negative realm of the y-axis. Therefore, these y-coordinates would be negative, okay? But note that this is our hypotenuse, so let's just indicate our right triangle more precisely. And again, although this is a right triangle, this angle being 90 degrees, we're still interested in this theta for our example that we're going to get to really soon, I promise, because this has nothing. Well, this is like the foundation for understanding the inverse trigonometric functions, okay? So it is kind of relevant. And just note that the hypotenuse or segment length will always be positive. This is how you find it. R is equivalent to the square root of the x-coordinate squared plus the y-coordinate squared. And as you can see, this is a variation of the distance formula. The neat thing about the angle being in standard position, the original angle, is that the vertex, which is the initial position for the segment length, is at the origin, which has a value of 0, 0. So we know that the distance formula is d is equivalent to the square root of x final minus x initial. Well, our x initial here is 0, so we don't have to indicate that. We're not going to be redundant. Then you square that. Then you add the difference between the final y position and the initial y position of the segment length. And here as well, because we're at the origin, our initial y position is 0, so the final y squared is going to suffice. We add these two together and, find the square root. Okay, so this is always going to be positive because what squaring does, no matter where your x and y coordinate is, it basically eliminates any negative signs. Okay. All right, so on to the next concept. The sine of theta, which we're going to use here in order to figure out what this inverse trigonometric function concept is all about, depends on the fractional ratio. Well, for this acute angle theta in standard position, it's going to depend on the fractional ratio of y, or the opposite side, over the hypotenuse, or r. So y over r, okay? And let's just say that our y coordinate value is going to be 1, okay? And our hypotenuse value is going to be 2. This would mean that the sine of this angle theta, again, is dependent on the fractional ratio of y over r. And in our case, in this specific example, it's going to be 1 over the hypotenuse length of 2. So here we have a known trigonometric value, as mentioned in the question stem. Well, how are we going to find the angle? Has anyone ever thought of that? Like, usually we have the angle and we find the trigonometric value, but we can also go backwards. If you have your handy dandy scientific or graphing calculator or Google, whatever your calculation device is, okay? All right, so one solution to this riddle is that the sine of theta can be transformed into the inverse sine. So this -1, what looks like a -1 exponent, indicates the inverse sine of some value k. Okay, and we don't know, well, the inverse sine of the value k is holding the place of our trigonometric function. And in our case, we know that the sine value is 1/2, so we're just going to go ahead and substitute k. This could have been x, y, but because x and y are used a lot in Cartesian coordinate geometry, k is also a standard variable used when holding the place of a trigonometric value for an inverse trigonometric function equation, okay? So we went ahead and plugged in our known trigonometric value, and this is equal to theta. So basically, in order to find the value of theta, all we did was take the inverse sine of both sides. And by taking the inverse sine of both sides, let me indicate this a little better. We took the inverse sine of this and flipped the equation around. And by taking, like, let's just pretend that this isn't here. I just wanted you to know what the sine is on a Cartesian coordinate plane when we're in quadrant 1 using the standard position concept. But when we take the inverse sine of the sine of theta, what it does is it undoes the sine function, and this gets eliminated. So that's why we end up with theta over here. And we flip the fraction around to make things flow a little better, okay? Not a fraction, equation is what I meant to say. And sometimes this expression is written as the arc sine of k, and again, our k is 1/2, so that's equivalent to theta. So these two expressions are synonymous, okay? They're different ways of expressing the same concept. Basically, what angle theta yields the sine value of 1/2, okay? All right, so hopefully you're not tired and you're still flowing with me. And basically, if our sine value, when you plug this into your calculator, you should get an answer of theta is equivalent to 30 degrees, okay? But remember earlier I mentioned reference angle? Whenever you're in quadrant 1, and then also we're going to put in the third side dimension, because if the fractional ratios of a triangle that has a 90-degree angle here and 30 degrees at the standard position is going to be 1 to radical 3 for the adjacent sides of 2. So this will be the fractional ratios, okay? But our answer was 30 degrees, but there may be another answer in quadrant 2, 3, or 4. But how do we know that? Well, there's definitely an answer in quadrant 4 because, you know, it's going to be positive 1/2. And then quadrants 2 and 3 would yield the negative 1/2 inverse sine values, okay? Or angular values. Now I'm just like all over the place in my speech. I apologize. I truly do. But I think you kind of get what I'm saying. Well, it's important to note that theta, our acute angle in standard position, is the quintessential reference angle. It's the positive acute angle formed with the x-axis, okay? But we can also have an angle over here, an obtuse angle. Let's say, let me show you what I'm talking about. Let's say we start here, go beyond the 30 point, sorry for my angle. And let's say this is our theta. Okay, that means that our terminal side array would end up right here, but this angle over here would be the reference angle. And I won't draw this concept again because the lag time is so ridiculous. But this would be our reference angle. So for this type of scenario, theta reference is basically equivalent to the extent of quadrant 2, which is the quadrantal angle, 180 degrees, that falls here on the negative x-axis, minus theta, theta being this huge obtuse angle. But let's say you know the reference angle, which we do in our case, let's say it's 30 degrees, but we want to know theta, then 180 minus our reference angle of 30 degrees would yield 150 degrees. So our obtuse angle in quadrant 2 would have will yield a sine value of 1/2, but negative 1/2. So this actually isn't a solution, but I just wanted to show you the concept of being careful about what angles, what quadrants you're in, and also assuming that there's only one solution when there might be a second, okay? Yeah, so let's take this to quadrant 3. If your terminal side rate ends up over here, again, the reference angle would be the positive acute, well, yeah, it would be the positive acute angle, because positive angles just grow in the counterclockwise direction. Form with the x-axis, and to find theta reference, we would subtract 180 degrees, which is the initial portion of quadrant 3. We would subtract that from the obtuse angle theta that would have a terminal side ray like somewhere over here, okay? But again, we know our reference angle is 30 degrees. So in this case, it would be the reference, theta would be the reference angle plus 180 degrees. So we would be dealing with an obtuse angle of 210 degrees. That yields a sine value of 1/2, but again, it's negative because we're in the realm of the negative y-axis. Oh, so actually, yeah, the solutions are in quadrants 1 and 2. Earlier I said it was negative over here. I was wrong because the y-coordinates are positive in quadrant 2, and our hypotenuse is always positive. But let's say you were to end up in quadrant 4. This is how you would calculate the reference angle. But since we know our reference angle, the way you would calculate theta, that corresponds to a sine value of 1/2, is to subtract 30 degrees, again our reference angle, from 360 degrees, the extent of quadrant 4, and we would end up with 330 degrees. So 330 degrees would have a sine value of negative 1/2 because our y would have to be negative, and of course our hypotenuse is always going to be positive, okay? So overall, in order to find an angle of a known trigonometric value, you have to use any one of the inverse trigonometric functions, whether it's inverse sine, inverse cosine, arc cosine, arc tangent, arc cotangent, inverse tangent, you name it. Okay, so the inverse functions basically find an angular value. All right. Intellectual comprehension of this material was not difficult, and after the short amount of time it takes to complete the entire cram session, you'll be prepared to answer a battery of questions about any Algebra 2 concept. So thanks for tuning in and good luck studying. Be sure to inbox me at memedicine@gmail.com to purchase the entire cram session.